Okay, so first of all, thank you for having me here. Super glad to be here, sharing with you our most recent paper, which is called "Are Optimal Algorithms Still Optimal?" and Rethinking Sorting Algorithms in LLM-Based Pairwise Ranking. It's done in collaboration with colleagues from Buenos Aires, and supervised by Luciano del Corro, which is currently my supervisor here in Argentina. All right, so I think I'm not seeing everything in my screen. I don't. Uh, that's better, I think. So you still are seeing everything, right?
Yeah, we can see everything.
Maybe, yeah, no, the best is this one. Okay. So maybe the first part of the talk will be a little bit boring if you already know about RAG, but in any case, we can go fast in this part of the talk. But it's important to give an introduction and motivation to the problem to understand why what we did is useful in a lot of LLM pipelines nowadays. So as you probably know, large language models can access external documents, and this is generally called RAG. The general naive RAG is to have a vector database and you embed a query and you have already embedded all the documents. You compare them through, let's say, cosine similarity. You have to choose which document embedding technique you will use. Maybe you use a BM25 or maybe you use neural embeddings from a sentence transformer, for example. And the good thing about this is that it leverages the current paradigm on LLMs. That basically means that we don't have to fine tune anything. We can make the model learn new information on the fly only by tweaking the prompt and choosing how to automatically choose what will go inside the prompt in a given LLM call. So in many real settings, we have collections of millions or billions of documents. It's infeasible to evaluate every document with a large model. A state-of-the-art model is not the best to evaluate each candidate document because current state-of-the-art models are super large. So we need this kind of naive approach of using a smaller model that embeds all our database of documents and then use a naive operation, which is cosine similarity, um, to make some kind of ranking between the documents and to understand if they are relevant to the query or not. But the problem is that they trade precision for speed, which means basically we will get a better ranking that just, I don't know, random sampling, but it will still have issues. In particular, maybe the first 1,000 documents are more relevant than the rest, but not necessarily I have the first 1,000 documents correctly sorted. Which means that I don't have a solution yet because I will need, let's say, in most settings, uh, 10 to 15 to 20 documents at most for the context length of the models. And for example, if I'm just in an information retrieval task without retrieval augmented generation, let's say I'm Google or another search engine, I have the same problem of having a limited context window to show to the user because the user won't be choosing a lot of results from the Google search, just the first ones. So the point is that this operation is cheap because I have a lot of documents, so I need it to be cheap, but it has problems. So here is an example of how this problem actually appears in practice. So let's say I have a query that says, generate a brief clinical report describing common respiratory conditions on domestic cats. So it's about veterinary. Okay. So the point is, I have two documents. The first one is about dogs, and the second one is about cats. But they share the same document structure, and they are completely analogous between each other. So probably you can imagine that for this given query that is about cats, the document A will be relevant. Maybe document B is also relevant. Maybe if my embedding model is good enough, document B is more relevant even, but document A will be very relevant. And it shouldn't be. It shouldn't be because it's not about what I want, even if the semantics are similar, even if the document structure is identical. So this is the kind of things that cosine similarity, which is the operation that relates the query and the document, will miss. It will say that the query and the document are similar when is not in the sense, they are not similar in the sense that we want. Another way to look at this problem is through the lens of recall and precision. When you do this called first stage retrieval, which is this naive first retrieval that we make, we will probably have a good recall on those first 1,000 documents, which essentially means that I have all the relevant information inside those 1,000 or 100 first documents after the first retrieval. But I also have, first of all, sorting problems because it's not ordered perfectly, but also I have a lot of noise inside those first 100 documents. I have a lot of noise, which formally we can say that we have low precision. So in an ideal case, when we finish the first stage retrieval, we have high recall and low precision. If we have high precision, then we are done. We don't need to re-rank documents. But if we have low precision and high recall, which is the most relevant case, then we introduce what is called a re-ranker. The re-ranker will be a more expensive process, but will be done in not 1 million or 1 billion documents. And the goal of the re-ranker is to have a better precision. So the point is that having high recall and high precision is costly in general, so I cannot afford it for all the documents at once. I need to do this two-step process. First, I have a lot of documents, I use something cheap. Then I don't have so much documents, I can afford to use something that is more expensive. Okay, so the point of a ranking is to, once I have the ranking, to make another ranking step over this smaller list of documents and to boost the precision. So we need the re-ranking because once we finish, we have precision, let's say precision at K with high enough, a high enough precision at K, enough to pass those documents into the context of the language model and expect a good answer, or pass those results into the first page of Google search and expect that the user finds what it needs. And the point is that the first stage retrieval uses simple similarity measures like cosine similarity that misses important points, and the re-ranking is made through relating the query and the document through a neural network. So instead of having a neural network and a neural embedding model that embeds the query and the document separately and then compare them through a naive operation that is cosine similarity, you make the neural network see at the same time the query and the document or documents and decide if they are relevant or how relevant they are given the query. And so since we relate the query and the document with a much complex model than just a cosine similarity between embeddings, we can catch more nuances. For example, a neural network could see that the important part of the text is that the user wants report about cats and not dogs. So the document about dogs is not relevant even if it's similar. The traditional re-rankers are the cross-encoders. Its name is because they are encoder models meant to receive both the query and the document and make for example, with a transformer, it would be cross attention between each other, but basically they will cross information between the query and the document to know if they are relevant or not. We have commercial cross encoders available through APIs. For example, we can import Cohere re-rank for our pipelines in RAG, or in Azure AI Search, we have a re-ranker made by the Azure team, and this technology is all around the web and used a lot in a lot of retrieval augmented generation pipelines. And the advantage of the cross encoders, of course, is that they are low latency. Disclaimer, compared to what, they are low latency, given that other techniques could be higher latency. Of course, they are high latency when we compare them to the first stage retrieval, but it's not like they introduce many seconds of wait in our programs. It's considered relatively efficient, and they are ready to use in production. But the limitation of the cross encoders is that they are small models trained to overfit data. And if you have complex documents, and if the ranking criteria is nuanced and custom, they start to fail, and they also introduce a risk. So the problem is, maybe your data is complex, maybe your queries are complex, maybe both are complex, and maybe it's not about complexity, but just being completely out of distribution, showing data that the encoder never saw. So they can fail, and we pay a cost, and there is a risk there, because we are adding a step on our pipeline just because if it doesn't work, then we are just paying more compute or more credits. So we must be sure that our re-ranker is giving us that higher precision, and if not, then we must remove it. Okay, so another paradigm that is being used a lot is, instead of using a cross encoder, why not just fitting all this into the current LLM paradigm, on which we basically say we don't want to fine tune for this task, we want to use a multitask generative transformer model. So there's a lot of papers that do this, basically do LLM-based re-ranking instead of using a specialized cross encoder. And basically, as you see on the right image, it comes down to defining a prompt. And in the prompt, you have to pass the query and the passages, the documents. And you have different prompts. For example, you have a prompt that would take only one passage or two or multiple. And depending on how the prompt is, we may ask for a score, or may ask for a binary, or it depends. There's a lot of ways to frame this concept, but the point is we are prompting LLMs to get a ranking over documents. So the point is, once we say that we don't need fine tuning, we start to see all the customization that is possible through prompting, because maybe in my queries I can add criteria, for example. So it's not only the query, but some specific criteria that I want to add to my ranking. And I can just add it to the query, since then the query will go inside a language model that is super smart, super intelligent, and will just read the criteria and order the documents accordingly to this custom criteria I just wrote into the query. So queries can be super complex and have rules inside, etc. And this is still kind of robust versus a cross encoder that if you write a super long query with rules inside, it will just fail. An early system for this application is RankGPT, which got published on EMNLP 2023. There is a repo, and you can use it. At that point of time, it used GPT 3.5 and GPT 4, and it was state of the art for re-ranking with GPT 4. when in the original table of the paper, you can see that they beat everything else when they try this prompting with GPT-4 for ranking. So the point is, this is much slower than a cross-encoder, but is strong and is robust, and it allows for customization without fine-tuning. So it's super valuable to have this type of things in pipelines, especially for lots and lots of companies worldwide that won't get into fine-tuning at all. And once a re-ranker that they imported from Azure Search or from Cohere Rank fails on their data, then they don't have any other choice. So regarding how to prompt it and what are the possibilities to prompt it, one is the pointwise. The pointwise means basically you ask if the document is relevant to this query, and maybe in the output format you decide like to ask the model for a score or for a binary. Is this relevant to the query? Yes or no? Or for a score between 1 to 10. So the problem with pointwise is one of the weakest prompting methods for ranking. And the main problem is believed to be that they have no context of other candidates. So relevancy is something that is more rich when studied relatively to other candidates. So if it doesn't have the other candidates, how will it know if it's relevant enough? So if there is no comparison in the prompt with other candidates, then the model struggles to understand the scale or the calibration that it needs to score the documents. All right, so listwise is the other way around. Basically, we attempt to put all the documents into the prompt. In practice, this is so only one LLM call would be needed because we pass all the query and all the documents, and we pretend the LLM to say the final ranking. Final ranking. Just you have all this unsorted list. Please sort it and give it to me. So in practice, that is not exactly how it works because we have context length limits and positional bias. So when you see pipelines that use listwise ranking with LLMs, what you see is that they end up making permutations for consistency and averaging results because they know that once the list is long, the list of documents is long, they will start to see positional bias, lost in the middle effect, recency bias, etc. So they have to permutate an average. And the other thing is, since the list is too long for the prompt, then they also have to do this like chunking and sliding window to pass into the LLM sets of documents instead of the full list. And the other disadvantage of listwise is that the task itself is harder. You can see that even if you don't have the problems that I said, the task is harder. If you ask a model to re-rank a list on a single prompt, expecting to have this thing that is completely unsorted, and the model has to reason on a single LLM call what's the final order, then it will make more mistakes. So those are two main prompting techniques for this re-ranking. In costs, okay, the pointwise would be like n LLM calls because you need to make one LLM call for each document, and in listwise would be constant or one, but you can also think about being constant. All right, and the pairwise, which is the scope of our paper is inside this prompting technique specifically, basically decides that we will compare two documents inside the prompt, and not three, and not one, and not the full list. At the right, you can see exactly the prompt that we use and the original pairwise ranking paper uses. So it's super straightforward. We will pass the query and we will ask which of the two passages is more relevant, and the output will be a binary. All right, so here we have a little bit of context for the model to not have to decide just looking at one passage. It can look at two and decide which one of those is more relevant. So we have more context. And we solved the problem of listwise that we have context length limits and a bigger positional bias. We have positional bias on pairwise ranking, but believe me that when I say that once you have 10 documents in the prompt, the positional bias is worse and worse. So this mitigates positional bias versus listwise, and also is a short, reasonable prompt. So it has some advantages. The main drawback of pairwise ranking prompting is the cost. I don't know if you recall from computer science courses that basically comparing all documents through pairwise comparisons will be n squared pairwise comparisons. So it's not constant, it's not linear, it's squared. So for example, with 100 documents, we would make 1,000 or 5,000 if we do consistency or something like that. But that is the order, in the thousands for the hundreds. Okay. So the point is that this quickly dominates runtime, and you are not in the case of the production re-rankers, cross-encoders like Azure Search, etc. And you added like a bunch of seconds to your problem, which makes your RAG super slow and not easy to put into production. But the performance is really good, and this is the promising part. Pairwise ranking prompting yields rankings that are very good, very strong. So that's the point. Despite the cost, PRP, pairwise ranking prompting, this prompting technique for rankings, achieves top performance against the other techniques. And this is on this table we are seeing is the original pairwise ranking prompting paper that went out in NACL 2024. And basically, the highest numbers, the highest performance numbers on the datasets are in the pairwise prompts against the original RankGPT. For example, with the RankGPT has a listwise prompt, for example, another pointwise methods that are here above this. So the best results were with pairwise ranking prompting. And also, I don't know if you noticed, but for example, GPT is meant to be used with API models, in that time, OpenAI models. But this technique is meant to be used with local models, and they use Flantify, which is an older generation model. Still, regardless of that, the performance is super nice. If I recall correctly, if you read throughout all the paper, you will have more tables, and the conclusions is like, the only thing that is competitive with this is RankGPT when it's used with GPT-4. Not even GPT-4 Mini. That didn't exist at the time, but they were using plain GPT-4. That was the only thing that beat this pairwise ranking prompting with Flantify. So the prompting part is strong, but the costs and the latency is super bad. Okay. If this concept of ideal model behavior basically means that the model may be wrong at some comparisons, but assuming that the model knows all the comparisons, is a perfect comparison, perfect comparator, then PRP guarantees a perfect ordering, and the problem is only the feasibility. So the authors of this paper for pairwise ranking prompting basically propose using sorting algorithms. They say something that is super basic, is we don't have to spend n squared, we can spend n log n because sorting algorithms exist. So why don't merge sorting algorithms with LLMs, since the prompt defines a comparator, and to be able to run a sorting algorithm, all we need is a well-defined comparator. So in the original paper, they explored two algorithms, Heapsort and bubble sort. Why they chose these algorithms? Because sorting theory has lots and lots of algorithms. So why they chose these two? Basically because they fit well with a property that is important for information retrieval and retrieval augmented generation. That is that in general you only want the top K. You have a list of documents, but you don't want the full sorted list. You want the top K sorted list, with K being a smaller number than all the elements of that list. And Heapsort and bubble sort, I don't know if you remember from computer science courses, but they have ways to stop at K. Early top K stopping, early stopping at K, whatever you want to call it. But the point is, in Heapsort, the invariant is basically that at the first step, you have one sorted element, which is the most important element, the rank 1 element. At the step 2, you have 2. At the step 3, you have 3. So you can cut the algorithm and just get the first top K at K times log n. Instead of n log n, you have K log n, with K smaller than n. The same bubble sort. Bubble sort is n squared in the worst case, but it achieves a much better performance with K times n instead of n squared if you stop when you have the first top K elements ranked. And what we notice is that they were biased towards this algorithm for this property, but top K is only one possible adaptation for efficiency that you can look, and maybe there's a trade-off. Maybe there's, because they chose these algorithms, there's another inefficiencies, and the top K efficiency doesn't pay for the other inefficiencies that they are adding. So to me, it was arbitrary at the time that Heapsort and bubble sort could be the faster and cheapest sorting algorithm, which motivated the investigation. So to this day, PRP is rarely deployed at scale. The main blocker is that it's expensive. Sorting documents drops down costs to n log n instead of n squared comparisons. But the insight is that actually sorting algorithms were not designed for LLMs. Sorting algorithms were designed to drop the costs of rankings, of sorting, drop the amounts of comparisons being made, yes, but not the creators of the sorting algorithms in the 60s, for example, they weren't thinking about the comparison being a massive neural network, super expensive. So that wasn't the cost model at the time. The sorting algorithms were meant to deal with comparisons that are cheap, in particular that are comparable to other CPU operations like swaps. And this is an assumption that doesn't hold in practice here, because here the only important cost is the LLM call, and all the other computational operations that I want to do are negligible against calling the LLM. So this distorts the cost model of sorting. Again, the point is, these authors saw that sorting brought down the costs for pairwise ranking prompting. But it's not exactly meant to do that. It gets things better, but they could be even better if we tweak the assumptions. So classical sorting algorithms assume that the comparisons are constant time operations that are equal in cost to other basic computations like swaps. And in PRP, comparisons are LLM inference calls that dominate runtime and resource usage against all the other operations. The cost asymmetry renders traditional complexity metrics meaningless, meaning that the cost model from sorting theory is not relevant to our case. So we need a new cost model that helps us understand which sorting algorithms are better for the ranking case. And in the original PRP experiments, Heapsort, the conclusion of the paper and following papers is that Heapsort is the best because it has super good performance, and the amount of comparisons that it does is minimal compared to other approaches. So since it required fewer comparisons and the performance was good, then this was the state of the art. Okay. Plus, they have the top case stopping property. But the problem of Heapsort is that you are forced to do one comparison at a time. Just because of the structure, the inherent structure of the algorithm, you cannot parallelize anything. It's fully sequential. To know which comparison is the next one, you have to run the algorithm and get to that point. There is no other way around it. So it's fully sequential. Does anybody have any questions?
Yes. Something about the pairwise comparisons that require to be well. I imagine that in order to be able to run a sorting algorithm using the neural network as a comparison assumes that the neural network implements a transitive order, a transitive comparison, right?
Yeah.
Is there any, I imagine that it's not very easy to impose as a constraint to the decisions of the neural network. What happens in practice when we run a pairwise sorting algorithm, with a neural network operator, when transitivity is not guaranteed?
Yeah, so that's actually in our future work. I will talk a little bit about that at the end of the talk. But basically, what happens is that you don't get perfect performance because models are just wrong. And as you said, they can be non-transitive in the sense that they assign that A is better than B is better than C, and C is better than A. So it's a loop. And that's the model's fault, because as a model that is intelligent enough should collapse the ambiguities into something that is the best that it can do at that time. So the point is, it's not the dataset fault. The dataset could have ambiguities, and maybe two documents are hard to rank between one another, but at the end of the day, you have to make a decision. Then if the model has inconsistencies in the output values that it gives with the comparisons, and it yields non-transitivity, then that's the model's fault. But the good property about sorting algorithms is that asymptotically, they are the best algorithms available because they have guarantees of correctness once the model is good enough. So all our approach can be re-implemented with newer and newer models, and since models get better and better each year, they will start, I guess that they will start having less inconsistency problems just because they are smarter. But yes, and how does it seem in practice? That is your question. Basically, you see that you at the end of the day, you have to measure the performance of the ranking. It's not like you're running a real deterministic sorting. You use a sorting algorithm for this ranking, but the ranking is not perfect. And at the end of the day, you measure empirically on retrieval metrics if the ranking is good or not. There is no other way to do it.
Wondering, how do you guarantee that the sorting algorithm terminates if there is no consistency in the ranking, the operator?
No, that is one that I don't know how to answer. Honestly, in our experiments, it always terminates, so we didn't have that problem. This is a theoretical problem that is very important, the non-transitivity, but empirically, I don't see it being a problem in everyday cases, because I ran this a lot of times, and for some reason, at least these ones, I'm not saying that you can expand the list of sorting algorithms, and probably you will find things that start to break because of the non-transitivity.
If I'm not mistaken, like these algorithms are guaranteed to terminate. It's like
they are, but he raises an important point, that is models may be inconsistent or non-transitive, which means that document A is better than B according to the model, B is better than C, and C is better than A. So it's a full loop.
Yeah.
That could break the sorting algorithm.
The thing is, if a sorting algorithm already computed A compared with B and B compared with C, this algorithm has no reason to compute A against C because it supposes transitivity.
Yeah, so you are raising another important point, that is most sorting algorithms are efficient, therefore they won't be doing that, and therefore that explains why empirically I don't get that case in every day. Yeah, that's totally true.
This means that a different starting order of the document can lead to a different
Exactly.
rank order.
Yeah.
After the ranking.
Yeah.
So what about, sorry, I have another question. What about, is like an upper bound fine tuning on the entire, like on the document and all possible passages that you could retrieve? Like, because you said one of the ways to use prompting for retrieval is to put all of the passages and then getting a rank like of all those passages in one go. Like, to me that sounds like it would be the best.
Yeah,
you can see all the interactions, but it's also the most expensive and maybe not feasible because of context length and so on.
Yeah, and the capability, because it's the best assuming that the model is capable enough, but
Right.
you can confuse the model.
I see. So is this usually like an upper bound that people use, or no, not really?
What is an upper bound? PRP?
Like this no, the what I just described as a prompting method with, like, if you were to fine tune that as well.
Yeah, there's people that fine tune on listwise, if that's the question. They fine tune on listwise. There's papers that do that.
Okay. And typically, does that perform better? Because I kind of just see that as like cross encoder versus bi-encoder. So does it perform?
It's one of the best techniques around, assuming that you can fine tune and you are okay with overfitting your model to your data, and if you have out of distribution data, your pipeline will probably break. Versus this approach that is super robust.
Okay, cool. Yeah. All right. Thanks.
Okay, so the cost model, as we see, the classic sorting theory cost model is basically the comparisons are worth 1 unit of cost, but for example, the swaps are 1 unit of cost as well. That doesn't make sense. So the new cost model, we are rethinking the cost model for these sorting algorithms, is the inference calls are the cost is 1 unit of cost. But we will consider that the inference call could be a call that I make in a batch. I will assume that I have access to a GPU. In my GPU, I have my re-ranker, and I can call the LLM with more than 1 prompt at the same time. And I will consider that as 1 unit of cost. This is a theoretical model. Of course, this doesn't happen in practice. I'm translating the theoretical cost model from classic sorting theory to a new theoretical cost model right now. So we will consider that one single LLM call, one code line that calls the LLM, even if it's in a batch of multiple prompts, then will be considered 1 unit of cost. And all other computations made in my pipeline, I don't know, storing something in a memory, in a dictionary, or I don't know, swapping elements in a list, will be considered to cost 0. So now that we have these cost models, what we see is that LLMs have trivial adaptations that we can see. The most straightforward, given what I said, is batching. LLMs allows batching. Of course, people like Sedgwick or Corman like the classical sorting theory guys weren't thinking about batching comparisons because the cost model didn't need this aspect. The other is caching. In LLMs, you have the classical trivial caching adaptation, which means basically you have a pipeline, you have an LLM call, and you have a dictionary at some point or a database. It doesn't matter exactly how to implement it, but the point is that you have, let's say it's a dictionary, and the key is the prompt, and the value is the output of the LLM. So each time I'm calling the LLM, I will check in the dictionary if I already used that prompt in the past or not. If I used that prompt in the past, then I don't call the LLM, I save that money, and I just return the value of that dictionary for that given key. That is a trivial adaptation. And the other one, the third one, is top case stopping, which is something that the previous papers already saw as important. So we have batching, we have caching, and we have top K. These are the three properties that we want to use to bring our costs down. The third one being one that is already on the scene. We bring batching and caching, and we combine these two with our cost model. What starts to happen is that the ranking of which sorting algorithm is more efficient starts to change because of the cost model that distorts the original costs that were presented in the original paper that said that basically Heapsort is the best. We start to see that if we enable batching, then Heapsort is not the best anymore because Heapsort is fully sequential. So if we enable batching, Heapsort cannot make use of that, but maybe other sorting algorithm can. Okay, so we introduce quicksort, which is another trivial algorithm in the sorting theory literature, but that nobody has combined with LLMs up to our paper. So all simple ideas that nobody has combined yet, but everything is simple. So what do we see in the image? What we see is that instead of having the original prompt template that had passage A and passage B, I have the same, it's literally the same prompt template, but in passage A, I'm like fixing a pivot because I don't know if you recall, quicksort involves for each step, find a pivot or choose it randomly, it doesn't matter, and compare all the other elements against the pivot and put the elements that are less than the pivot on the left and the ones that are greater than the pivot on the right. So now we can make a batch call to the LLM with all passages against a pivot. So this is the same pairwise prompt, but we can parallelize all these comparisons. Quicksort allows for this, while Heapsort doesn't. The other figure, the figure on the right, is about bubble sort. This is a little bit more nuanced, and I'm sorry if you don't remember bubble sort, you probably have to read a little bit after to understand why this happens, but if you remember bubble sort, basically you bubble up the elements from the bottom to the top. So basically you start with this 4, you compare with the 3. In this case, they want the small numbers on the left. So 4 is compared to 3, and that pass is over because the 4 is well placed against the 3, so that stays the same. The 3 is compared with the 2, that stays the same. The 2 is compared with the 1, that stays the same. And the 1 is compared with the 10, and that triggers a swap, and the 1 will bubble up and be on the left of the 10. So we repeat that this pass over all the list, we have to make one pass. We have to make at most, in the worst case, n passes. So what bubble sort has is a big inefficiency, big inefficiency that makes the 4 and the 3 to be compared more than once, because in the first pass, I compare the 4 and the 3, but they don't swap. And in the second pass, I compare the 4 and the 3 again, because I always start from the bottom. How do we fix that in classic sorting theory? The answer is we don't. What Cormen would say, or Sedgwick, or the original people that work on this would say, is you don't solve it. because in the moment that you start to solve it, you will spend the same amount of cost than if you leave it like this, because a comparison is worth 1. And a memory that could tell you if you already did that comparison or not, accessing it is linear. Or if it's an array, is the same, it's 1. So why would you fix this? It doesn't need to be fixed. This is the most efficient you can get with bubble sort according to the classing theory. But according to our cost model, having a cache has negligible cost because the only important thing is the neural network. That is the only cost. So we implement a cache. And when 4 wants to be compared with 3, we don't call the language model anymore because we saved it on step 1. So this is the cache used to bring costs down in bubble sort. And at last, the point is, okay, Heapsort doesn't have batching properties. I cannot modify Heapsort to be parallelizable. Heapsort is inherently sequential. It doesn't have caching because it inherently doesn't repeat comparisons ever for any reason. So that's an efficiency of Heapsort, not to repeat comparisons. But what I mean here is that I cannot make it better through caching. I cannot do anything with caching with Heapsort. With bubble sort, we don't have batching, but we can apply caching. And of course, we have top K because the original papers already chose Heapsort and bubble sort because they have top K. And quicksort has batching, doesn't have caching because it doesn't repeat comparisons. And it does have top K. The original authors used the Heapsort and bubble sort because they are the algorithm that everybody knows that allows this top K early stopping. Everybody knows that Heapsort and bubble sort are the examples of top K stopping. But reading through the sorting literature, I found this guy Martinez that formalized this partial quicksort sorting algorithm that basically brings costs down of quicksort by allowing only to get the sorted top K instead of the full sorting, which is not a very well-known thing, but I said, okay, the point here is if I want to have an impact with my paper, I want to maintain the only efficiency property that the original authors had. So I want top K, and I want to implement my new efficiencies. And this can be done. I don't have a lot of time. If I had, I would explain exactly how partial quicksort works, but it's not relevant. The point is that you bring cost down further from the original quicksort because you can have only the top K and not the full sorting. Okay, so how efficiency changes? In our paper, we show that if you have a big batch, here we have a plot with the batch size on the x-axis, we start to see that quicksort costs, according to our cost model, goes down even like 95% if I have a 128 size batch. So again, this is, in a way, this is trivial, but the important part and the lesson from our paper to me is that nobody have found this, that it was trivial, because they were using a theoretical framework that was off. Once you see that the theoretical framework doesn't fit what you're trying to do, immediately you see that quicksort is the correct choice. So if batch size is 1, Heapsort is still the most efficient. These are some conclusions. If you have batch size, even batch size equals 2, then use quicksort. So those are some of the conclusions that you can draw from this. This plot is theoretical. It's based on literally counting the LLM inferences one by one, because our cost model is literally summing 1 for each LLM inference that you do. But this plot is more empirical, because we know that batch size doesn't reduce latency proportionally. The speed up is not proportional. As you can see in the plot, We used some GPUs to try this empirically, and we see that, for example, for an A100, we have proportionality, which we call ideal speedup, up to batch size 8. Then you start to see diminishing returns, but still you have better latency, better speedup than using batch size 8. So you start having diminishing returns, and according to the size of the GPU, the diminishing returns come at a lower point of the plot. So once we had all our theoretical cost model and we counted how the algorithm should perform, we actually used the GPU and counted the latency, the seconds exactly, to see how much our theoretical model fits what we see in practice. And what we see is that up to the ideal batch sizes for each GPU, our cost model fits what we see empirically. And when the diminishing returns start to appear, then our cost model starts to distort a little bit, but still makes a lot of sense as a theoretical cost model, a simple cost model that allows you to just see an algorithm and try to infer rapidly if it will be good for LLMs or not. Then our cost model makes a lot of sense. And bubble sort is amazing, but almost half of the comparisons were repeated. This is amazing. When I started, I noticed this property of bubble sort that repeated comparisons, but I never imagined that on the cache I would see that almost 50% of the inference calls were cache hits. And it doesn't require a lot of memory because just saving some prompts and outputs on the memory while you are doing the sorting algorithm. And you're assuming that your list is like at most 1,000 documents. So it's just a dictionary with text. So the ranking quality question, we measure the quality with NDCG, and what we see is that we don't know exactly why yet, but it doesn't matter really much which algorithm you choose. There is a case on which it matters. If the first stage ranking is very bad, then, for example, bubble sort is poor. While if the first stage rank is very good, then bubble sort is the best. So what you can see is that bubble sort is efficient when the list is almost sorted, and is inefficient if the list is on the opposite, like inverse sorted or something like that. But again, if you assume that you have the first stage ranking and it's reasonable, which it is in these data sets, then you start to see that the differences are not statistically significant. So this makes us think that the most important variable to choose an algorithm is the latency or the cost, and not the final performance. So in practice, which algorithms you should use? In general, quicksort with batching, especially if you want to go into production with this is the only thing that is realistic, in the sense that you could expect that it doesn't waste, 20 seconds. If no batching is available, then Heapsort or bubble sort with caching, because bubble sort used to be more expensive according to the original paper, but once you add the cache, actually is competitive with Heapsort, which is another observation and another finding of the paper. And for top K, well, they all work, but again, the decision-making variables should be if you have or not have batching available, and if you have some assumption of how well the first stage ranking works. Maybe you can choose between Heapsort and bubble sort better, but it's not exactly clear yet. The point is that bubble sort used to be considered as costlier than Heapsort, and now it's not clear, so they are kind of in a tie. I'm finishing the talk. I have technically 1 minute, but the future work basically is to explore other algorithms that, for example, handle non-transitivity inherently inside the algorithm, and also statistical ranking algorithms, because sorting algorithms are still expensive, n log n. But there is statistical ranking algorithms. Let's think, for example, a super simple example, but the World Cup, the soccer World Cup, you make different teams to play, and they don't play against each other, and they don't do sorting. They do a minimal amount of matches, and you still get a winner. But kind of you lose information, so there's a trade-off, and maybe the winner is not the correct one. So there's a whole amount of literature on statistical rankings that are like another family of rankings that are in opposition to sorting, that is correct in the computational sense. They finish with guarantees, but this will help. This would help us to bring the cost from n log n to linear, so it makes sense to explore. I think that a lot of papers will be published in this field. For example, this is super promising and got published in October 2025, so a couple of days ago. And we will see more papers like this, but it's not exactly easy. The reason why we don't see a lot is because sorting algorithms actually perform really well. So it's not like you implement a statistical ranking algorithm and you win, because the rankings are kind of saturated and the sorting algorithms are really good.
Okay. Thanks, Juan. We're kind of out of time.
Yeah, no worries. The only part that I missed is the future work, but no worries.
Okay. Then yeah, but anyways, yeah, one question.
Like last question maybe. So you had the graph like where you were comparing like across different benchmarks, like the sorting algorithms that you have used, and this is like a performance like a 10 DCG at 10. Have you noticed potentially? I assume that there is the same underlying model across all of these algorithms. Do their performance change depending on the first stage top K?
Yes, the first stage ranking.
Yes. Does the performance in then DCG at 10 like depend on top K? Top K. Yeah, like and the algorithm of sorting simultaneously.
I don't know if I understood the question, but if the question is if the sorting algorithm behaves differently depending on the first stage ranking, then the answer is yes.
Right. So like if you specify, for example, right now, I don't know, you have like a fixed top K. If the top K was double, would the order of like those sorting algorithms change? Would it affect the like which one performs the best like with a given model? Are you talking only value?
What's the setup? You have a top K, and I have the top K, and what do I do?
Now, like fix a benchmark, for example, and like you have like I don't know the top K being 64. You run with your model like the pairwise like sorting algorithm. You choose bubble sort and Heapsort. You see consistently that bubble sort is better. Then you double the top K. Now it's 128, and you see that then this G of 10 is better suddenly for Heapsort. Like
I double the top K. What does that mean? To concatenate, to do what exactly? What is to double the top K?
The first stage ranking is going to have like more documents to sort. It's going to bring more documents for
Okay.
ranking to sort.
No, I didn't try what happens if you change the K on the first stage ranking and which one of these is better. No, that I didn't try that. No.
Right. I was wondering that because of the previous question with the inconsistencies, like in the.
No, what I can say is that, again, if you, for example, invert the first stage ranking, let's say I use BM25, but instead of showing to the re-ranking step the inverted BM25, then Heapsort is much better than bubble sort. So Heapsort would be more robust to bad first stage rankings. But in opposition, if the first stage ranking is super good, then the most robust The one that breaks less the already good ranking is bubble sort.
Interesting.
Okay, I think with that note, we close the session. Thanks, Juan, for coming. And yeah, congrats on the paper. Yeah.
Thank you, and thank you all for having me, and good luck.
You can reach out Juan. I'll leave Juan's email somewhere. Where should I leave his email?
On the Slack channel.
Yeah.
On the Slack channel. We have a Slack channel.
Yes, we do.
I'll leave Juan's email on the Slack channel. We are recording this, so we should upload it at some point. I will let you know once it's uploaded.
Thank you a lot, Thomas, and thank you, everyone.
Okay, thanks a lot.
Bye-bye.
Bye, have a good one.
See ya. Nice. Okay.
Nice. Oh, this one?
Yeah. And the recording, where do you access this?
Bye, everyone. Bye. Everyone else.